great junior session by Qingtian Zhang. He talked about uniqueness of conservative solution to the Camassa-Holm equation via characteristic.
First, I would thank the organizers to give me a chance to speak here. And today, my talk is about the uniqueness of the conservative solution to the Camassa-Holm equation. This is a joint work with Alberto Brisson and Geng Chen. Camassa-Holm equation is an approximate model to describe the motion of the water wave. Here, U is the average the horizontal velocity, and this P is pressure. But since here there is no divergence-free condition, so this P is given by the convolution term of these two terms. And also, by using the Fourier transform, you can rewrite P as the pseudo-differential form. And there is several equivalent formulations for the Camassa-Holm equation. And if you take this pseudo-differential operator to the first and second terms, you will get the second formulation. And furthermore, if you assume V to be U minus the second derivative of U, then you can write the equation as the so-called the Euler alpha model, but it is just a variant formulation for the Euler alpha model. And for smooth solutions, all the three formulations are equivalent, but here we prefer the first kind of formulation. And the energy of the Camassa-Holm equation is like this. We can, if you take the time derivative of E, then we can prove that this energy is preserved by the smooth solution. And we can see from here that this energy is something equivalent with the H1 norm of the U. So generally speaking, we expect this U to be in the H1 space. And in fact, the typical solution of the Camassa-Holm equation is like this. We can prove that under some special conditions, we can find the derivative blow-up for the Camassa-Holm equation. And this blow-up can be considered like this. This result is being proved by Adrian Constantine and Escher, and also by McKean. And we can consider two waves of the Camassa-Holm equation. One wave is approaching from the left to the right. Another wave is coming from the right to the left. And if these two waves approaching, and then the middle part of this solution U will become approaching to the vertical. So after they approach, so we will get the first order derivative blow-up here. We can consider this mechanism as this way. First, we have a beacon here, and there is another beacon here. If they approach each other, we only consider the middle part of this wave. And after some time, the solution will become this way. So we can see that this part will become more and more vertical, and finally, the solution will become, the middle part will become approach to infinity. So this is a fundamental, this is one kind of fundamental mechanism for the blow-up of the Camassa-Holm equation. Because there is this kind of blow-up for the classical solution, so we cannot expect the global existence for the classical solution. So here, the most natural way to think about the global solution is to consider the global weak solution here. And the global weak solution has been proved by several groups by using different kinds of methods. Generally speaking, we have these two kinds of methods to prove the global weak solution. The first method is by using the vanishing viscosity method. This result is proved by Ping Zhouxin and Ping Zhang in 2000. And for this kind of solution, furthermore, they can also prove the one-side estimate for the Camassa-Holm equation. And I will explain later that their solution, the solution funded by the vanishing viscosity method is a dissipative solution. And the second method is by characteristic method, and this method is proved by Alberto Bresson and Adrian Constantine in 2000. And in fact, they constructed two kinds of solution. One is the conservative solution, and another one is dissipative solution. I will explain these two kinds of solutions later. And the methods they use here is to construct a semi-linear system along the characteristics, and they change the variable and to consider another variable. And in the new variable, the solution is well-posed. And then they come back to the original equation, so they construct a solution to the original Camassa-Holm equation. But because they just construct the solution, they lose the uniqueness for this Camassa-Holm equation. And another result is proved by Holden and Reynolds, and they also proved the unique existence of the Camassa-Holm equation by using the Lagrange coordinates. And there are some other results for the initial data by Constantine and Asher, and also Constantine and Monilate in 2000. And because their initial data is very special, so it is not the general initial data here. And for the uniqueness of the solution, it's mainly proved by these two methods. And the first method is result about weak-strong uniqueness. It is proved by Xin and Zhang in 2002. And their result is some similar result about, related with the compressible Navier-Stokes. Because here, they assume the first-order derivative of U is in L-infinity space, and this L-infinity norm can be controlled by a L2 local function of time. But as we mentioned before, the energy of the Camassa-Holm equation is in H1. So generally speaking, this norm is too strong to prove the weak solution here. And the second method is by using the optimal transport distance. And in the paper of Bresson and Fontaine in 2005, they construct an optimal transportation metric. And they prove that the difference between two solutions and this metric will not grow too fast. And they can always find a control for the distance between two solutions. But this result is only we used to call this result is the stability result, because if we want to prove the uniqueness, we still use these tangential conditions here. And this condition is not easy to check for all conservative solutions. And this is the result by Brunant, Holden, and Reynolds in 2011 and 2013 is very similar. They also construct another kind of distance function, optimal transport distance function, to get the stability. But there is still some gap to get the uniqueness. And the 2005, this result is on the torus, and the later result is on the real line. And now, our result is the uniqueness by characteristics. In our results, we do not need any further assumptions to the initial data or other case. And this is our main theorem here. For any initial data in H1, we can prove that the Cauchy problem of the Camassa-Holm equation has a unique conservative solution. And here, I will introduce a little bit about what is the conservative solution and the dissipative solution. Let's try to still look at this picture. If we consider two waves with the equivalent strength, then this part and this part is symmetric. Then, after a short time, these two waves will approaching, and until this curve, this middle part will be vertical. But the Camassa-Holm equation is different from the Burger's equation. In Burger's equation, this will form a shock. But in the Camassa-Holm equation, because we have the conservative of solution reaching H1. So generally speaking, the U is in Holder 1/2 space, and the solution will become about like this way. This is when this peak and this valley meet each other, and the solution will become in this way. And here it is still continuous in this point. And after that, if these two waves come out from this point, then we say this kind of solution is a conservative solution. You can regard this conservative solution as the cross of these two waves. But there will be another case of the solution which is in this way. If you consider the two waves has equivalent strength, then at this time, when they coincide with each other, what you see in the graph will be only a zero at the straight line. But here, the energy is now zero because there is an energy concentration here somewhere. It is an energy concentration like a delta function. So if after this point, the solution will become a zero, then we say this solution is energy dissipative solution because the energy concentration delta disappears suddenly. So this is two kinds of solutions. And here, what we prove is the uniqueness for the energy conservative solution. It is this kind of solution. And this is just the mathematical formulation for the definition of the energy conservative solution. And the main idea is in this graph. And the difficulty for this problem is like this. We can write down the equation for the characteristics because as I just mentioned, the U is only in H1. So when we write down the equation in this way, we can say that this U is in H1, or we can also write it as this U in Holder 1/2 space. This space is still far from the Lipschitz continuity function. So here, for the ODE, with the right-hand side is Lipschitz continuous, we can prove the existence and the uniqueness. But for the ODE with the right-hand side, it's not Lipschitz continuous. It's only Holder continuous. We still have the existence, but we lose the uniqueness here. So this is the difficulty for this problem. And we can see the characteristic line like this. Generally speaking, there will be this condition here. The characteristics will be tangent to each other. And when they tangent, if you consider any other characteristics between these two tangent characteristics, you will see that all the other characteristics between these two characteristics will also passing through this tangent point. And when they come out, you will lose the uniqueness here. So we will need to find a correspondence between the incoming characteristics and the outgoing characteristics. This is the main point here. And we consider to solve this problem by the following way. We define the change of coordinate here. We change the x to beta. But here, I prefer to show you the second lemma first, because from the second lemma, you can see that this is the equation for the characteristics. Because only this equation we cannot prove the uniqueness of the characteristics. So here we add another condition here. When we combine these two conditions, we can prove the uniqueness. And the second condition has the physical meaning here. You can see here, this is the one part of the energy. The whole energy is U squared plus UX squared. And because here, the bad part is only the derivative part. So we only take the derivative of the energy. And this part of the energy is to the left side of the characteristics. And the dynamics is look like this. If we combine these two conditions, then we can prove the uniqueness for the characteristics. in fact, you can see that if we consider the characteristics, the energy on the left side of the characteristics, then the characteristics will be uniquely determined. And after we have that idea, then we can consider the lemma 1. The lemma 1 for this transformation, we just add the two parts together, and then we can get the new variable beta. And under this new variable beta, we can prove that the dynamics of the beta is determined by this equation. This is just by the calculation. And the good thing is that the right-hand side G is Lipschitz continuity. It is Lipschitz continuous with respect to the new variable beta. So here, we can conclude that the equation for beta is well defined. We have the existence and the uniqueness. And then we shall consider the main theorem. We want to prove that along the characteristics, we can construct a system. And for this new system, the right-hand side is Lipschitz continuous. And in fact, under the new variable t beta coordinate, we can prove that all these things is Lipschitz continuous. So all this derivative is well defined by using the Rademacher theorem, which says that if the function is Lipschitz continuous, then the derivative exists almost everywhere. So we can rewrite the system into t beta coordinate. And there is a little trick here. Because for this term appears in the expression of p. And we do not have this derivative of u sub x because, as we said before, u is not Lipschitz continuous with respect to x. But we can recover u sub x by using this fraction. This is because u sub beta and x sub beta are both well defined. And then we can rewrite the system like this way. This is the equation for beta, and this is the equation for u. And v is the arctangent of the first order derivative of u. And if we rewrite this system into this, we can find that the right-hand side is Lipschitz continuous. So we got the uniqueness for the whole solution. Okay, this is what I want to talk today. Thank you.